let's look at the tangent to a curve, because this concept has something to do with limit of difference quotient as well as a derivative that you are going to learn a bit later. Okay, so when we talk about tangent to a curve in geometry, if you have a circle like this, all right, so a tangent to a circle is defined as a line that has one point in common with the circle. So in this case, let's say this point A. So you draw this straight line. This straight line becomes tangent to this circle. I give you another example, not only a circle, any kind of curvy curve, okay, as long as it's not a straight line curve. So let's say I have here X here, and then Y here, and then I have something like this, which is similar to, if you can remember in your principle of micro, we call it production possibility frontier or curve, PPC or PPF. Okay, so if we have a line, a straight line that, touch one point here, at least one point here, so call this point point B. So this line is actually the tangent to the curve here. I get a tangent. So here, but then if I show you this, okay, in this figure, all right, so we start with point A, okay, point A here, and then we move to another point here, Q1, connecting point A and point Q1, then we have a line called S1. This line is below the curve. This line basically is not a tangent because it intersects the curve, okay? So because it intersects the curve, so because like I said just now, it's not a tangent line, then how do we call this line? This line is what we call second line. Okay, second line. Now, if I pick another point here, Q2, and then I join it with the point of A, then I get another second line, call it S2. I pick another point, Q3, connected with A, I got the third second line, S3, and so on and so forth. Can you see? From S1 to S2, S2 to S3, S3 to S4 until the L, okay? You can see that the second line, the distance between the new point here and point A, okay, becomes smaller and smaller. And then if you go further, then you can see the distance is actually can't be seen because it's exactly at point A, which is this curve. So this curve basically is a tangent to this, this curve. This straight line is a tangent to this curve at point A. All right, now let me erase the mess here. I want you to look at this important thing. If we have point A and Q1, which is on second line 1, so this is Y, this is X, yeah? And then I'll show you this. Okay, at point A, you have coordinate of A, let's say X1 and then Y1. At point Q1, you have coordinate of another coordinate, call it X2, and then Y2. We can calculate the slope here for second line 1 because we have 2 points, isn't it? So we call it M1, the slope for the first second line, which is Y2 minus Y1 over X2 minus X1, isn't it? Okay? But if we have another point here, another second line, another new point Q2, then I can have another one here. You have 2 points. So this one I call it X3. This one I call it Y3. So we have 2 points, Y1, X1, Y3, sorry, X1, Y1, X3, Y3. So we can have the second slope Y3 minus Y1 over x3 minus x1 in it. Okay, and you can see here second line compared S2 second line with S1 second line. Which one is steeper? The steeper one is S2. If it is steeper, logically speaking, the slope for the second one must be higher in value, isn't it? That one you can replace with number. Let's say this one is 1, this one is 5, this one is let's say 2, this one let's say 3, then you can calculate this. You can see clearly the slope of the second line for S2 is higher than the slope of S1. Similarly, you can do it for S3 and S4. So you can get slope number 3, slope number 4. The slope number 4, logically speaking, will be higher than the slope number 3, and then will be higher than the slope number 2, will be higher than the slope number 1. But my main point here is to show you that once we have many second line, as the second here, move closer and closer to the tangent line, you can see that the value of, Q1, Q2, Q3, Q4 approaches A. Alright? So when it approaches point A here, that means Q1 here, X2, moving to X3, X3 becomes closer to X1, we have another one here, X4 becomes closer and closer to X1. So basically, when the X value here becomes closer and closer to, X1, then we can see the denominator here becomes smaller and smaller, isn't it? Alright, smaller and smaller. And almost, 0, but not 0. So when I say become smaller and smaller, and the difference here becomes smaller and smaller because x here becomes closer and closer to x1. So the distance here becomes narrower and narrower. The distance here refers to the distance, the difference. So when the distance or the difference becomes narrower, alright, we are telling that, we are basically talking about the limit. Okay, when x here when whatever x here approaches x1, then the difference here becomes almost 0, isn't it? So that means the difference here, x2 minus x1 or x3 minus x1 or x4 minus x1 here, moving from here to here to here, so on and so forth. So let's call this one is change in x, this one also change in x, change in x. Change in x here becomes smaller and smaller. Okay, when the change in x becomes smaller and smaller, alright, then we are basically talking about taking limit. Okay, taking limit. That has something to do with the limit that we have learned earlier, this one. Okay, r prime x and whatnot. Okay, so that one I'll show you more later, yeah. Alright, so I want to be more detailed about the calculation of slope here. As you can see, if we have one second line like this is second line and not a tangent. You can see if I pick one point here, I want to come up with a tangent, then it should be like this. You can see the tangent here. Tangent compared to second line intersect the curve. But tangent doesn't intersect the curve. Tangent only has one point that is touching the curve but not intersecting. If you say intersecting, this one, this is intersecting. But if you say tangent, this is tangent. Okay? Alright. Now you look here, we have 2 points. Let me erase the mess first. See this mess, put it away. Alright. So the first point is here. The second point is here. So with the first point, you have x1. And then this one, fx1, or we call it y1. The second point here, you have x2. Therefore, here you have fx2 or y2. Now, the difference between x1 and x2 here, I call it h following the textbook. So here, x2 here can be said x1 plus the distance here, which is h, x1 plus h, isn't it? So that means I can rewrite this as f x1 plus h, isn't it? Okay? Alright. Now, if I want to calculate the slope between these 2 points, then it must be, the slope must be fx2 minus fx1 over x2 minus x1, isn't it? Or y2 minus y1 over x2 minus x1. Now, because I can rewrite this as this, then I can say fx1 plus h minus fx1 over x x2, x2 minus x1, which is h. Okay, so this is similar to this. So what I want to say here is that when we go back to this graph, so when the q here, this is the first q, the second q, the third q, so on and so forth, is approaching point A, you can see the h, okay? The h here becomes smaller and smaller, isn't it? I mean the distance between A and Q horizontally becomes smaller and smaller. And I make it clearer like this. So if you have x here, y here, and then you have this, and then you have point A, and then you have the first, second line, Q1, okay? So the distance, okay, is the first H, okay? And then let's say this is a tangent line, Q3 for instance. Then we have another Q, another second line, Q2, and then we have another different H here. So I use a red pen. This is another H, which is red H. Okay. Then you can see the red H is actually smaller than the black H. The red H is actually the change in X, isn't it? The black H is also the change in X. Alright, so as a consequence, the denominator here becomes smaller and smaller, and therefore you can see that, okay, move further, the distance becomes smaller and smaller. Alright, and then you can see the first second line moving to the second one, moving to the third one, it approaches the tangent line of A. Alright, so that means the slope also, from one second line to second line to the tangent line, the slope also approaches the slope of tangent line at A. This is tangent line. Alright, so when I say approaches, then that means we are talking about the slope in which it is closer and closer to the slope of second line, which is closer and closer to the slope of tangent line. Therefore, we are talking about limit. We can see here the limit of h becomes smaller and smaller, and as the second line approaches tangent line, the distance of h here becomes smaller and smaller and become almost zero. Alright, so that's the slope of tangent line. So what I'm trying to say here is that the slope of tangent line at point A is actually the limit of this ratio, okay? And this ratio is actually what we call difference quotient. Why it is called difference quotient? Quotient means ratio, difference means this is the first difference on the numerator. This is also different on the denominator, because this one is actually the change in x. This one is actually the change in y. Okay. Alright. So the slope of tangent line is nothing else but the limit of difference quotient as h approaches 0. Limit of difference quotient as h approaches 0. If h doesn't approach 0, let's say limit of h approaches 1, then we are not talking about the limit of difference quotient equivalent to the slope of tangent line. We are talking about different thing. You get what I mean here? So again, the limit of difference quotient as h approaches 0 is actually the slope of tangent line at point A, and that is also known as derivative at point X. Okay, so let me erase the mess here. What I'm trying to say here, this slope here is actually the slope of tangent line equivalent to the limit of difference quotient as h approaches 0. And that also means derivative at point A, which is this notation. Okay, when x equivalent to x1. This one is x1. Okay, so I hope this is now let's look at the example here. We want to find the slope of tangent line. Okay, at one particular point. So given this exercise, y equal to fx equals to 3x squared plus 2x plus 11. So question A, find the derivative of fx at any point x fx. Because we haven't studied a specific formula for derivative, which will be studied shortly, then we need to use limit of difference quotient to find the derivative. Remember in the previous graph, I did use the example here to show you that the limit of difference quotient is actually the derivative of the function at a particular point. So we use limit of difference quotient to answer these questions. Okay, so how to do question A? We know that, okay, the sign of derivative is f prime x, okay, also can be rewritten as y prime. So we use the limit of difference quotient, limit as h approaches 0, and we know that the general formula is this, isn't it? So how do we write it specifically using this function? So I continue here, equivalent to limit as h approaches 0. Fx plus h is basically, look here carefully, 3x plus h squared. Okay, so you see 3x squared becomes 3 in bracket x plus h squared plus 2x. 2x becomes 2x plus h plus 11. Okay, then I make a square bracket. So the whole thing in the square bracket is actually this one. Okay, and then minus fx. So fx is the whole thing here, so you just need to rewrite them again. But don't forget to put bracket because you are not changing the sign here. So a 3x squared plus 2x plus 11, close the bracket, divided by h. Okay. And what you need to do next is to expand this. So, and also to expand this. So to write it again here, limit h approaches 0. So in bracket 3, okay, when you expand it becomes, it means x plus h square is exactly equivalent to x plus h times x plus h, isn't it? So here x plus h times x plus h becomes this, x squared plus 2xh plus h squared, close the bracket, and then plus this When you expand, it becomes 2x plus 2h and then plus 11. Okay, so I close the bracket and then here I want to open the bracket, yeah. So 3x squared minus, because minus meets plus becomes minus, so 2x minus meets plus becomes minus also for 11. Okay, and in fact here I don't need to put the square bracket also because it doesn't change the sign. And divided by h. Okay. Alright, now continuing the next line, so I continue here. Then it becomes, okay, limit as h approaches 0. So you simplify further. When you simplify, it becomes 6xh plus 3h squared plus 2h, right? So h. And you can further simplify this. Then we can rewrite it this way. Limit of h approaches 0, so it becomes 6x plus 3h plus 2, isn't it? Now, when we consider h approaches 0, then we are left with 6x, no longer writing limit as h approaches 0 anymore, yeah? Because now we are trying to approximate h equivalent to 0. So 6x plus 2. So that's the final answer for A. Okay. Let's crack on. We look at this. Question B. Find the slope of the tangent to the curve at 1 and 16. So here, the derivative itself, I mean this answer, is also called slope. Then if we have a coordinate of, from the question, which is 1 and 16, so we have 1 and 16. So the slope here, okay, is what? The slope, or f prime x or y prime, is actually, you substitute x equivalent to 1 into this derivative, and then plus 2, and then you get 8. So that's the answer for B. So I have answered question B. Now move to question C. We have found slope. The equation of tangent line to y equivalent to 3x squared plus 2x plus 11. So perhaps, yeah, because I haven't checked how does it look like. So let's say it looks like this. So let's say the point is here. Let's say, I'm not sure whether it looks like this or it looks like this. It needs another topic to determine whether this function looks like this, you know, like a bowl, or like this, upside down bowl. But anyway, let's say it looks like this. So we put one point. That point is, let's say, 1, 16. Okay. So 1 is here, 16 is here, y is here, x is here, yeah. So at this particular point, we draw a line, a straight line, that becomes a tangent to the, you know, the bowl here at point 116. So if you go to question C here, find the equation of the line tangent to this curve. So we need to find this equation, the equation for this line. To find the equation for the line, like so here, general equation for any line is y equivalent to mx plus c. So you have point 116. Also, you already have found m, which is f prime x equivalent to 8. So with this information, you can plug in into this general, you know, equation to find the answer for C. So what here we can do here is that so we have 8, and then we have 1, and then we have 16 here. Then we can find what is C, isn't it? So here, if you rearrange it, C becomes 16 minus 8 equivalent to 8, isn't it? So here, then the equation of tangent line at 116 for you know, y equivalent to 3x squared. Let me check the equation. 3x squared plus 2x plus 11 plus 2x plus 11 is this, yeah? So y equivalent to 8x plus 8. That's it. Okay, so we have answered this. Okay, right. Now, when we get derivative from the previous question, if you can recall back, 6x plus 2 equivalent to y prime, or can also be rewritten as f prime x. Okay, what does it mean by this? And at 116 coordinate, we have found this one equivalent to 8, isn't it? What does it mean by this? How do we interpret it? So interpretations of derivative here, for a given function, each of the following means find the derivative. Derivative is also termed as velocity when an object moving in a straight line. Okay, so let's say this is a road which is straight. Then you have a car. Okay, and it moves straight here. What is the velocity? Okay, find the instantaneous rate of change of a function. Instantaneous rate of change is also derivative. Find the marginal revenue for a given revenue function. Find the slope of tangent to the graph of a function. So basically derivative in economic study most of the time, okay, let's say we have utility function. If you find the derivative of utility function, that derivative is what we call marginal utility. So if we have revenue function, if you find the derivative of revenue function, that one is what we call marginal revenue. And if you have cost function, you find the derivative of the cost function, then the answer is what we call marginal cost. Or, mathematically speaking, it is basically the slope of the tangent to the graph of a function like what we did just now. In calculator, most of the calculator has this either one of these function, so can be derivative can be found from calculator. But if you ask me personally, I prefer student to know the method to calculate derivative manually. All right. So the method to calculate derivative manually, it has different types of method because it depends on the function that we, the premier, the primary function and the primal function that we have. Okay, because we have certain number of rules to find derivatives that we should follow. So this is the thing that we're going to do in the next slide. Let's look at one important concept on differentiability, that is differentiability and also continuity. All right. There are some functions for which their derivatives do not really exist, yeah, for at a certain value of x. Okay, let me show you by having some graphs here. Let's look at the first graph here. You see c is here, the value of x, which is c, is here. Before c, you can see the graph is continuous. But at c, one value of y is here, let's say call it y1. Another value of y is here, let's call it y2. So you have two value of y's here, and you can see the gap. Therefore, we have discontinuity for this graph at point C at x equivalent to c. So at x equivalent to c, if you try to put tangent line and try to calculate the slope of tangent line here, it won't happen. Where do you want to put it? Is it here or is it here? Do you get what I mean? So if you're talking about here, then you see the tangent line is upsloping, then you would expect the slope to be positive. But here the slope will be negative. So it is contradicted to each other. As a consequence, because of this discontinuity at point C, at x equivalent to c, then it's not possible for us to find the slope for c here, and therefore when we can't find the slope here, therefore m here does not exist, then this one is not differentiable. All right. let's look at the second graph here. The second graph here, you can see C is here, x equivalent to C is here. Before C, the graph is downsloping. After C, the graph is upsloping. You don't find any gap. But at point C, you can see the corner or kinked point. And although you can see along the curve here, all points are continuous, isn't it? Including this point at the kink point. However, at the continuous point at point C here, we have kinked. So is it possible to be differentiated? You try to draw also the tangent line here. It could be this or it could be this, isn't it? So which one? So we can't find the differentiation, different derivative value here. So it's not differentiable at point x equivalent to C. Okay? But at this point, you can find the slope. At this any point along before C, you can also find the slope. Now, let's move to graph number 3. You can see no gap, so we can say that it is continuous along the curve. But let's say we look at point x equivalent to C here. At this point, when you try to draw a tangent line, you're going to have a vertical tangent. If you have vertical tangent, when you try to calculate the slope, see here, you have two y's, y1, y2, isn't it? So C stay the same. So when you calculate the slope, y2 minus y1, but C1, C2 minus C1, C2 minus C1, C doesn't change, so that means C2 equals to C1. So that means C2 equals to C1, the denominator here is 0, regardless the value here, sorry. So let's say the value here, the difference between y2 and y1 is 5. Okay, so 5 divided by 0, you're going to get infinity value. So the slope is very, very steep, perfectly steep, such that cannot be differentiated because it, you see here, it gives you infinity value. Here, graph is curvy, but you have vertical tangent here also, okay, and you have kink point. Let me erase the mess so that you can see what I mean. Oops, sorry. So here, if you can see the mess, I'll delete it, and you can see kink point here. So when you have kink point, it's not differentiable at x equivalent to C. So you can see graph number 1, you have, gap. When you see the curve like this, let me erase the mess first. When you see the curve like this, you have gap here. We call this kind of curve as a step function, step curve, because you have step between this and this. This one is continuous but not differentiable at point C, x equivalent to C, because you have kink point here. This one also has kink point at point x equivalent to C, not differentiable. Although both of them, graph number 2 and also graph number 4, both of them are continuous. Yeah, the curves are continuous. So, but this one here, you can see continuous as well at point C, continuous as well, but you have vertical tangent. Then vertical tangent give you infinity in answer of slope, so it's not differentiable. So these cases here, what we can say here, as long as you have discontinuity like the first case, corner like the second and the fourth cases, or kink point, or also vertical tangent like the third case, then, alright, we cannot differentiate the function at that particular point. Alright, so here, basically, what we can see, let's move to the next one. Function can be continuous at x equivalent to C, but sometimes it cannot be differentiated, so you cannot find derivative. So if you have this, continuous, isn't it? And then you have C here, You have x here, you have y here. Continuous, so that's why you can find derivative at this point. So that means in order for a function to be able to be differentiated, first thing is must be continuous. But not all continuous function can be, you can find derivative or can be differentiated. That means continuous is necessary for a function to be continuous, but not a sufficient condition. Okay. Differentiability implies that the function is continuous. Otherwise, if we cannot differentiate, could be the function has a gap, isn't it? But based on case number 2 and also number 4 just now, continuity doesn't mean that it can always be differentiated all the time. That means continuity is a necessary condition for a function to be differentiated, for a function to have derivative, but not a sufficient condition for a function to be differentiated. Okay? Now we move to derivative formulas. Here, in this slides from A to E, okay, if I'm not mistaken, we have the 7 rules of derivative. And before I proceed, remember when you learned about the limits of difference quotient, and then the continuity and whatnot, those have something to do with derivative, because derivative itself is a slope or a point at that particular a slope of a point at that particular point, not between 2 points. Yeah. All right. So that's why it's called limit of difference quotient, or rate of change, or gradient, okay, or slope. So this is derivative. All right, now, so let's look at some formulas of derivatives here. All right. So let's say if we have a function in which we have fx is a function of x raised to the power of n. So you can see here, if you have y, which is fx, y depends on x, and in that equation you have x, which is raised to the power of n. So the exponent of x here is n. So how are you going to derive a derivative or a slope? So the symbol of derivative here, you can write it y prime, or you can write it f prime, or you can also write it this way, delta fx over delta x. Okay, so this, you can either use this symbol, or this symbol to signify derivatives here. So let's say we have this. So you see the variable here is raised to the power of n. Then we can use what we call powers of x rule. Okay. So if we have this, then what we should do here is this. F prime x is actually, you bring power n here and become a constant here. And then x, rewrite it again. And then x to the power of n becomes what? X to the power of n minus 1. Okay, minus 1. So always minus 1. Alright, now let's look at example. For instance, I look at example A. Example A, primary function is u as equivalent to s to the power of 8. So if you want to find the derivative, write the symbol first. U prime s, you look at the way I do step by step, yeah? You have s to the power of 8. This power of 8, bring it here next to s, so it becomes a new constant attached to s, isn't it? And then rewrite again the power 8 here, and then minus 1. So it becomes 8s to the power of 7. Okay, so I've done A. We have, for example, here, let me pick another one here. Let's say C. Okay, so I write a line to differentiate it. So I'm doing C. So my C here is Ct equivalent to square root of t. Before we proceed to the differentiation, finding derivative, let me rewrite again this function in another form. You see the square root here? It can also be rewritten as, this one is not derivative here, I just rewrite again the function in different way. Ct equivalent to t raised to the power of 1/2, because 1/2 here is equivalent to square root, isn't it? Then we can easily use powers of x rule to differentiate it to get the derivative. So now we can proceed with the process of getting the derivative, which is write the derivative symbol c prime t. You can also rewrite it this way: delta ct over delta t. Okay, you get me? Like I said earlier, you can also write it this way. Okay, so it becomes what? The power here 1/2, bring it to the left, attach it to t, becomes a constant here. T, rewrite it against the power of half here minus 1. Okay, so when you do that, you're going to get 1/2 t minus 1/2, isn't it? So don't leave it just like this here, because this is incomplete basically. Although the answer is correct, but for me it's incomplete. So you can rewrite it this way: 1/2, because t is raised to the power of minus 1/2, so that means t can be rewritten in the denominator area, and then minus 1/2 becomes positive 1/2, but it must be on the denominator. So that's the final answer. So if you stop here but you don't continue here, then your mark will be less, even if you get right answer, because this is how I differentiate between A and A minus, student. What about this? Try to do it on your own. What about this? Try to do it on your own. For this, try to transform the the expression into another different way of writing equation before you find derivative. So obviously, you can see here, you can make it this way. All right, minus 1/2, isn't it? Then you can use powers of x rule. Okay, so make sure you know how to get from here to here, because this one is a typical thing that you learn in the high school. Okay, so that is the first one, but we move to the second one now. Okay, and the second one here is this. Let's look at the derivative of a constant. Okay, the derivative of a constant. Okay, let's say your function here, you have y as a function of fx, but in your answer you don't see x, you just see a constant number or a scalar. So this is what we call constant function. Okay, a constant function, when you try to find a derivative, it is always equivalent to 0 because you don't see x here. Okay, so what should we do? We can actually prove this. If you can recall back, the limit of difference quotient is this formula. Alright, so as the h approaches 0, so for instance, if we put it in the form of graph, if we try to visualize it in which this is a constant, let's say y equivalent to 5. Okay, so y is here, let's say x is here, so let's say 5 is here, so that means it's a horizontal line, isn't it? When it is a horizontal line, y equivalent to 5. So even if your x here is 2, or your x here is 5, your y is always 5. So here 2, 5, coordinate here 5, 5, isn't it? So if you try to calculate the limits of difference quotient, then you can plug in here. Alright, so you have this one is fx, this one is fx plus h, isn't it? So when you try to find the this, you can have limit of h approaches 0 equivalent to fx plus h is what? 5. Okay, 5. Fx is what? 5 minus 5. Okay, h is what? H is actually change in x. We have 5 minus 2. So here 3, but this one is 0. Still your answer is 0. Can you see? So without going through all of this hustle and bustle here, straightforward, if you see a constant, let's say y equivalent to 5, so when you find derivative, just go straight to 0, because it has been proven by this example here. Okay, so this is a constant function rule. Constant function rule says if fx is equivalent to c, where c is a constant, then f prime x is 0. Straightforward, get it 0. Okay, that's it. Now we move to the next derivative here, in which we have y equivalent to c constant, or a scalar, multiplied by a function a function that depends on x. So basically here you have y as a function of x, and then there you have constant, then times a function, specific function. So I'll give you example here. So here, if fx is c multiplied by ux, in this case ux is gx, my own writing here, where c is a constant and ux is a differentiable function of x. Why it is differentiable? Because in that you can see x. Then f prime x, or derivative of fx, is actually c, constant, stay the same, but you differentiate the ux as usual using rules. Okay, whatever rules do you have, suitable rules that you have learned. Okay, so the coefficient rule says that the derivative of a constant times a function is a constant times the derivative of the function itself. Constant times the derivative of the function itself. So let's look at the example here. We have three examples. Let's pick example A. A, original function, we have fx equivalent to 4x squared. So you can see constant here, and then you can see a function here, because x to a square here is a function. So this one we can consider it as ux or gx here. So it means if you want to get it, you know that it is like this: c times u prime x, isn't it? So for this case, if you try to answer, this is how you answer it. So originally fx equivalent to 4x squared, isn't it? But if you want to find derivative f prime x, or can also be rewritten as this, yeah, delta fx over delta x, then constant stay the same, leave it just like that, but multiply by what? Multiply by derivative of this part. Derivative of this part, because you have learned the power rules, you can use power rules to solve it. But if it is different kind of function with x, which you can't use power rule, you use different rule that you learn later. Okay, so for this one you can use power rules. Alright, so bring 2 here, attach to x, and x to the power of 2 minus 1. That's it. And then you simplify it further, it becomes x to the power of 1, but we never write this way, isn't it? So 8x. So that's it. Okay, so this is example A. Similarly, with this example and this example, I want you to try it yourself. Okay, now let's move to the next rules of a derivatives of sums and differences. Okay, the sum and difference rules are for the derivatives are as follows. So let's say you have some rules. If you have y equivalent to fx, in which you have inside there you have ux plus vx, then what you can do is that y prime equivalent to f prime x here is basically equivalent to u prime x plus v prime x. That's it. You just differentiate as usual. But if it is minus, then simply change it to minus sign here, minus. That's it. Okay, then we can have difference rule. Now, why don't we look at the example here? This example, sum and difference rule. Let's look at example A. Okay, example A. Example A, you have y equivalent to 3x plus 5. In y equivalent to 3x plus 5, let me rewrite it in here. Y equivalent to 3x plus 5. If you refer back here, you see addition here. Okay, this addition. So that means y in general, okay, is equivalent to ux plus vx. In this case, ux is this, and then vx is this. You get me? So how are you going to find the derivative? For ux, constant times x, then you can use this coefficient rule, isn't it? Because c here is a constant here is a coefficient. Okay, coefficient or parameter. That's the term used. Okay, and then for the vx here, what rule can you use? Because you don't see x attached to 5, then you can use derivative of a constant function rule. Okay, let's do it. So it means in this example we have 2 derivative rules that we need to apply. Okay, for question A. So here, question A, y prime, or can also be rewritten as f prime x, is equivalent to 3 times x, 3 times x to the power of 1, 1 minus 1, bring 1 here. Okay, I'll do it one by one, but in fact, some students who are very good, they don't have to do something like this, they don't have to do something like this, because it's just 1. Okay, but here I'll show you one by one, so those who never learned this before can easily follow it. Okay, we are done with u prime x. Now we are doing v prime x. V prime x, because it's just a constant without variable x, so you apply constant rules here, constant derivative rules. So here 5 with x is 0, so it becomes 0, isn't it? So here you have 3x to the power of 0 plus 0. Okay, so that means 0, that's the first one. And then 3 times 1, because x to the power of 0 means 1, isn't it? Equivalent to 3. And actually, if you're very good in maths, you don't have to write this step. You just go straight to this. Okay, alright. So for instance, if I have another one, y equivalent to 12x squared, okay, plus 6, then I have y prime equal to f prime x. Either one you can use, y prime or f prime x. So you have 12, bring to here, x to minus 1, and then you know this one is 6, 0, and I can get 24, okay, so yeah, plus 0, 24 plus 0, it becomes 24. That's it. Okay, I hope this is clear. Alright, now let's look at another more practical example. Okay, but before that, if let's say this one is, instead of plus, it becomes minus, right? So what you can do here is that you simply change it to minus sign. Okay, minus sign. That's all. Okay, that's it. Alright, now, so let's look at an example here. So if we have the horizontal tangent, for instance, fx equivalent to x cubed plus 3x squared minus 45x plus 4, where the tangent line is horizontal. So find all points on the graph. It means find the coordinates on the graph. So when you have this equation, you draw the graph. Maybe it looks like this, maybe it looks like this, I don't know, we haven't seen it. And then if it looks like this, like I said, the graph here, if you draw a line that just a tangent, not intersect, that line can calculate the slope at that particular point, where we call it derivative. Okay, so, and the tangent line is horizontal. Now if horizontal, it means like this, isn't it? So it means the slope of this point. Okay, so what's the solution? So that means, so if you can recall back the lecture, x, y. So if you have fx like this, and then you have fx, this is 1, a, b, and then you have like this. See, for the first one here, the slope is steep, isn't it? For the second one here, the slope is a bit flatter. For the last one here, the slope is very, very flat. When the slope is flat here, the slope is actually 0. No slope because it's flat. So when the tangent line is horizontal, that means the slope is flat. Slope is equivalent to 0. And I told you last time, derivative is the slope. So f prime x is the slope. When the slope is 0, slope is flat. That's what it means by horizontal line here. So that means if you have a curve, let's say the curve looks like this, or the curve looks like this. So when you want to calculate the slope, this one is not flat. The tangent line is not flat. This one is also not flat. But this one is flat. So the slope here should be 0. This one is not flat, steeper. This one is not flat, steeper. But this one is flat. So here the slope is flat. Is it clear? Alright. So in this case, we need to find the slope first. Once the slope here is found, set it equal to 0 and then rearrange it to find x. That's what it means by this question. Is it clear? So let me erase the graph first so that it won't be in a mess. Okay. Now here, to have this, first, find derivative. So here we have so many functions. So here, you see here, let's say the first one here is ux, the second one here vx, the third one here gx, the fourth one here hx, for instance. So you have to differentiate 1, 2, 3, 4. Okay, 4 different sub functions in fx. Then you set it equal to 0. So here, once you do it, this is how we do it. Okay, x cubed, when you differentiate it, it becomes what? Let me use the same pen so that you're not confused, because I'm doing continuation from here to here to here. X cubed, you differentiate it, it becomes, bring 3 here, attach to x to the power of 3 minus 1. Okay, I'll do it one by one. Okay, next we need to differentiate this. This one is vx, like I told you just now, isn't it? So we have done the ux. This one is basically u prime x. This one is the vx. So I'm doing v prime x. So this is, the coefficient, derivative rules. So because we have constant here attached to x, so write the constant as the same. Because x to the power of 2 or x squared, bring 2 here and then x here 2 minus 1. Okay, so this one is actually v prime x. Like I told you, this one is gx. So you need to find g prime x. So write minus. So this is coefficient, derivative rules as well. So here we have 45, write down minus, and then x here 1, and then 1 minus 1. Why? Because this one is x to the power of 1. Okay, let me write it clearly so that you can see clearly, otherwise it becomes a mess. So 1, x, 1 minus 1. Now last one here is hx. Okay, plus here, write plus here. So hx here, because it's a constant, no x is attached, we can use constant, rules for constant. Derivative of a constant function rule. This function, which is hx, okay, this function which is hx is a constant function. So here it becomes 0. So this one power, this one coefficient, this one also coefficient, the last one here is constant. So this one is actually h prime x, isn't it? Okay, this one is actually g prime x, isn't it? Alright, so now you can simplify it further. So it becomes 3x squared plus 6x, okay, minus 45. X to the power of 1 minus 1 becomes x to the power of 0, which is equivalent to 1. So I don't have to write 1 here. I just write minus 45. And then plus 0, I don't have to write 0 here. Okay, you got me? And then don't forget to set it equal to 0. Remember the question here, find all points. So find all points means we need to get coordinates. Coordinates here you have a and b. This one is x, this one is y. Okay, so here obviously you can find x first, then only once you find x, then you can find y. Okay, so before we can find x, what you can do here is that, see this, we can simplify it further to make our life easier when it comes to finding x by factorizing it first. So here common factor is 3, isn't it? So it becomes x squared plus 2x minus 15. Okay, then equal to 0. So 3 here, bring here, it becomes 0. So you can have x squared plus 2x minus 15. How to get x here? So to get x here, this is quadratic function. You can factorize it like the way we did previously for quadratic function. So here you can have what? You can have, when you factorize it, x plus 5 and then x minus 3. I'm not going to show you how to get from here to here. Yeah, this is a very high scope work. Okay, now because I don't have enough space, so I make it this way. So I move from this is the first step, second step, the third step, the fourth step. I move to the fifth step inside the small square here or rectangle here. Then I can find x plus 5 equivalent to 0, or x minus 3 equivalent to 0. So if it is x plus 5 equivalent to 0, so x here is minus 5, and here x is equivalent to 3. So remember, this is unfinished work because you need to find all the points. So once you find x equivalent to minus 5, what is y? Once you find x equivalent to 3, what is y? You need to find the y. So basically, you have two coordinates. The first coordinate is A, the second coordinate is B, isn't it? So in this case, let me erase some area here, yeah, so that I have space to do the work. Okay, so I erase this. Okay, now I continue here. Yeah. Okay. So here for A, when x is equivalent to 3, y equivalent to 1. Okay. So here you need to substitute it back because you want to get coordinates. So you have 3 and then f 3, isn't it? When B, when x equivalent to minus 5, y equivalent to 1. So basically we need to find 5 and then f5, isn't it? So if you substitute it back into original function, which is this one, x equivalent to 3, then you try it at home, yeah, and then you check whether you get the same answer or not. So then the first coordinate you're going to get is minus 5, 179 for A, and then this one, if you substitute x equivalent to minus 5, okay, no, wait a minute, sorry, yeah, this is wrong. This is the other way. This is correct. Sorry, wrong actually. This one is actually for the second one. This one is for the second one. Minus 5, 179 is actually for the second one. I wrongly look at the different x. So this one will give you minus 5, 179. And here, how do you get minus 5, 179? Because minus 5 we substitute it back into this function to get y. Same goes to A. A you have 3, and then here when you substitute x equivalent to 3 back into the original function, yeah, then you get minus 77. So these are the two coordinates, the points on the graph in which tangent is horizontal. Now, if you know how to draw the graph, of course, now you don't know how to draw this kind of graph because it's complicated. It's a cubic function. If you don't believe me, let me delete this bit so that you can see that clearly that it's a cubic function. So you can see clearly it's a cubic function, isn't it? So usually there is a way to draw it, but let's assume that you have done it. So when you have done it, this is how it looks like. So you have 2 points of x minus 5, 179 that you have found earlier, and then you have 3 minus 77. At this point, the tangent line is flat. The curve looks like this, yeah? Looks like, you know, many parabolas. This is the first parabola, this is the second, but if you extend, you may have more parabola, like, you know, like a wave. But here, for simplicity, you can see, because we just talked about 2 points here. Alright, so here, minus 5, 179 is here. 3 minus 77 is here. So that means, you know, these two points are basically a point in which tangent line to the curve are flat. Tangent is not intersection. This is intersection. This is tangent. Just barely touch. This is intersection. This is tangent. The question is about tangent line. Tangent line can help you to measure the slope of particular point, one point, instantaneously. Okay? Alright? So this is how it looks like. Okay, so that's the answer. There is another, application for, for this calculation. When we talk about slope or the rate of change or gradient, if you have, this function, let's say y equivalent to fx, and then you find the derivative. This function could be revenue, could be profit, could be total cost, total utility, total marks. When you find the slope is actually the marginal of this function. Okay, so here you need to learn how to use it for application and how to interpret it. That's what I mean. So let's pick one example, economic example, which is marginal revenue. The marginal revenue R prime X is used to estimate the change in revenue caused by the sale of one additional unit. Yeah. So let's look at proper examples so that you can clearly see it. Revenue. Suppose that a manufacturer of a product knows that because of the demand for this product, his revenue is given by this. This is revenue 1500x minus 0.02x squared. So x here is the number of units sold or the quantity, and Rx is the revenue in terms of dollars, in terms of pounds sterling, ringgit, and whatnot. Find the marginal revenue at x equivalent to 500. If it asks you to find the marginal revenue, it means, mathematically speaking, you have the original revenue function or the primary function. When it asks you to find marginal revenue, it means it wants you to find slope of this revenue function. Once you find the slope of this revenue function using derivative rules, then you insert x equivalent to 500 to get the value of the slope in number form rather than leaving it with x, okay, with x only. So how to do it? So first you need to find marginal revenue function. Marginal revenue function is also the slope of the revenue function. I'll explain you more about the concept after this, but first we need to find it. So you see here, and then you see here, we can apply this rule. You see the subtraction here, the difference. So we can apply derivatives of differences. Difference rules is this: if fx equivalent to ux minus vx, then we do this. Okay. So here, so you have fx, which is Rx, this one is Ux, and then you have minus, and then you have Vx. Can you see? This and this. Okay? So you apply Ux, you differentiate Ux. This is coefficient or a constant multiplied by variable x. So you use coefficient derivative rules. In this case, 1500x becomes 1500. Okay? Minus stay the same. So you have coefficient also here, alright, a constant, write the same. X squared, you differentiate it, bring 2 here, and then x 2 minus 1, okay. And then you have 1500 minus 0.04 x to the power of 1, or just simply x, okay. Now, next what should you do? Of course, this is the marginal revenue, okay. But if we want it to be at x equivalent to 500, what should we do? Just substitute x at x equivalent to 500, then it gives you R prime x, or marginal revenue, equivalent to 1500 minus 0.04 times 500. Then you solve it, you're gonna get positive 1480. Positive 1480 is your marginal revenue. But how do you know how to interpret it? Basically, that's what I mean. So in this case, when you have marginal revenue equivalent to 1480, it means if I increase, x equivalent to 1 unit, if I produce and sell one additional unit of x by one additional unit, or by 1 unit of x, I sell it, then my revenue, because it's positive here, then my revenue will increase. Positive means increase by 1,480. So that means what? Produce more to get more revenues, isn't it? All right. So this is one example. We can also have, let's say, marginal profit. If you calculate profit equal to revenue minus cost, isn't it? Then if I ask you what is marginal profit at x equivalent to 10, this profit function, find the derivative, and then insert 10 back into here. And then let's say your answer is 400. It means what? If I increase the sale of X quantity by the amount of 10, by the amount of 1, additional 1, then my profit increases because it's positive, increases by 400. But if let's say you get minus, it means my profit will reduce by 400. You're making more losses. Do you get me? All right. So that's it. And then next we continue with the product rules and also quotient rule. Let's look at product rule first. Okay, so product rule here is that if we have a function that gives us, let's say, this generic function, fx equivalent to ux multiplied by vx, so it means within fx you have two explicit functions, ux and also vx, where u and v are differentiable, means that this one can be differentiated with respect to x. Then what we can have here, in order to find marginal function or slope or instantaneous rate of change, which is this, okay, is this. First, you hold this one constant, you differentiate this, so it becomes ux multiplied by v prime x. Then add plus, and then hold this one constant, differentiate this, then it becomes vx multiplied u prime x. Okay, so let's look at the first example. A, find dy over dx if y equivalent to this. Okay, but before I proceed, in the previous slides, I did mention to you that if you have this, you can also rewrite it like this, or you write it delta y over delta x, or delta fx over delta x, isn't it? But here, if you can see, it uses d instead of delta. What does it mean? When is the right time to use d? When is the right time to use delta? Okay, if you see here, y here depends on only one variable, which is x. This one is differentiating the whole function with respect to one variable. This one also differentiating the whole function with respect to a variable, in this case, because only have x as your independent variable. However, this kind of sign, okay, is actually giving us meaning of total derivative. This one gives us partial derivative name. The title, the name here, the term here is partial derivative. This one is total derivative. So what's the difference? You have function that depends on x. So when you want to find the slope, you can either write this way or this way. But if you have a function y equivalent to f, x, z, w, for instance. So in order to see the impact of x on y, then you have to use delta y over delta x. You can't use the dy over dx because you have not only one independent variable that gives impact to y, but also another 2 here. So this one is actually for the whole thing. This one is for partial. For this case, in this case, you can see clearly it's only y as a function of x instead of x, z, w, isn't it? So instead of z, x, w, so you only have x. That's why it is allowed to use this. If your independent variable is only 1, yes, you can use this as your partial derivative, or you write this way. Is it clear? Okay, now let's go back to product rule because we want to solve the question now. So don't use a wrong sign for slope and for any other mathematical symbol, yeah? Because it gives you different meaning in mathematics, it's wrong. Okay, now when we talk about product rule here, find product rule if your y here is like this. So your y here is like this. So call this first one ux, the second one here vx. Okay? So how are you going to do it? So here, let's say I rewrite again the equation here. Y equivalent to 2x cubed plus 3x plus 1 x squared plus 4. So you know that this one is ux, this one is vx, and you know the formula in general looks like this, isn't it? Y prime equivalent to ux, differentiate vx first and then leave vx just like that and then differentiate u, isn't it? So let's do it one by one. So here is how we should write the answer. Y prime, or you can also rewrite it this way, dy over dx, or you can also write it, let's say this one is fx, you can have it like this as well, equals to, okay, you rewrite ux as usual, 2x cubed plus 3x plus 1, but you differentiate vx, so vx here becomes 2x plus 0, isn't it? X squared, you differentiate, becomes 2x plus 4. 4 here, when you differentiate, because it's a constant, no x, it becomes 0, and then that's it. So you see here, plus sign, plus, okay, plus. Now next, we write again vx here, x squared plus 4, but differentiate ux. So when you differentiate, don't forget to put bracket, yeah? 2x cubed becomes 6x squared. I hope by now you should know how to get 2x cubed from 2x cubed to 6x squared when you differentiate. And 3x becomes 3, close bracket. And then now I move here. Proceed with solving the whole equation. But yeah, the whole equation is here. So this one, is this basically 4x to the power of 4 plus 3, okay, plus 6x squared, 6x squared plus 2x, because 2x cubed times 2x becomes 2x to the power 4, because this is power 3, this is power 1, 3 plus 1, 4, isn't it? Okay, and then the rest. Okay, we are done with this one. This plus, we write it again here. Now, expand this. When you expand, okay, so you have x squared times 6x squared becomes 6x to the power of 4. X squared multiplied by 3 becomes 3x squared. This and this, isn't it? Now, move to this one. 4 times 6x squared becomes 24x squared. 4 times 3 becomes 12, isn't it? And then you solve it even further, simplify further, 10x to the power of 4, 33x squared plus 2x plus 12. Okay? Alright. Now, there is another example here, example B. At the point where x equal to 1, find the slope of tangent to the graph of this. So the slope of tangent at x equivalent to 1, how do you find it? So that means from y here you need to find y prime or fx prime, isn't it? So because you have here 1 and 2, let's call this one ux, let's call this one vx, then you have to use product rule here. Product means multiply, okay? That's why you can see it's multiply the derivative with the original function of another function, okay? Product. Okay, now, so how are we going to do it? Let's see here. Let me rewrite again the function y equivalent to fx equals to, let me check again here, otherwise I may write the wrong one. not this one, this is quotient rule. Okay, 2x cubed and sorry, 4x cubed. Okay, 4x cubed and then this one. Alright, now here let's do it. So 4x cubed plus 5x squared minus 6x plus 5 in bracket multiply by x cubed minus 4x squared plus 1. That's it. So y prime at x equal to 1 is equivalent to what? That's the question. So now we need to find my prime first. Equivalent to f prime x equals to 1. So here, let's say this one is ux, this one is vx. Okay, so you rewrite here, okay, u again, 4x cubed plus 5x squared minus 6x plus 5, but you differentiate vx. When you differentiate vx, it becomes 3x squared, isn't it? X cubed becomes 3x squared minus 4x squared becomes 8x, isn't it? Close the bracket. Why? Because you don't, when you differentiate one, it becomes a zero. Constant rule, yeah? Okay. And then let me clear the mess first, otherwise you don't get what I'm doing. Okay, so minus. And then don't forget plus. Now we rewrite again vx, but we differentiate ux. So when we rewrite vx, it becomes x cubed minus 4x squared plus 1 and then in bracket differentiate ux. When you differentiate ux, 4x cubed becomes 12x squared plus 5x squared becomes 10x only. Minus is minus, I'm talking about this. 6x becomes 6, 5 becomes 0, and then close the bracket. And then next, you have done the differentiation or found the derivative, but you don't leave it just like that. Because we want to find the value of derivative at x equivalent to 1, you substitute all x here with 1. Okay? When you substitute all x here with 1, then you may have 4 1 cubed plus 5 1 square minus 6 times 1 plus 5, close the bracket, okay, like the way I did it before, and then 3 1 square times 1 square minus 8 times 1, close the bracket, and then plus, okay, 1 cubed minus 4 1 square multiply plus 1, close the bracket, multiply by 12 times 1 square plus 10 times 1 minus 6, isn't it? So when you calculate it, you're going to get this 8 times minus 5, okay, for the whole thing here, plus, which is this plus, so and then minus 2 16 for this one. Okay. Then when you total up, it becomes minus 72. Let me erase the mess. Okay. That's the answer. So when you have the slope of tangent line at x equivalent to 1, the slope is actually minus 72, means downsloping with the value of 72. So if x increases by 1, okay, y will decrease by 72. That's how we interpret it. Okay, so that's done for product rule. Now we move to quotient rule. Quotient rule, you have to look at it very, very carefully, because some of the students may find it difficult to do when you are dealing with ratio. Okay. But before that, yeah, if we look at this answer for quotient rule for question A and B. Let's look at question A. Question A. So I stop here, isn't it? I stop here. If you think that you can, this is the final answer, but if you think the final answer, you can simplify it further by factorization or whatever to make it look nicer, then proceed. But this one, obviously, you cannot simplify further because 10, 2, and 12, they may have common factor, which is 2, but 33 is not having common factor with the rest. It has to be common factor for all. So you cannot factorize, you cannot simplify to make it nicer. But if you can do it, don't leave it just like that. Is it clear? Okay. Now let's move to quotient rule here. Now for a quotient means you have a ratio, division. Okay. Now let's say you have this fx equals to x cubed over x. So you tend to simplify it further by having x squared, then it won't be quotient anymore, isn't it? But if we have something like this, fx, then when it is no longer quotient, then you don't apply quotient rule. You just simply find f prime x equivalent to 2x, isn't it? Which is using power rule, isn't it? So here, when we involve with quotient rule, you don't simplify for and one the example of quotient equation is 2x plus x plus 1. Okay, so this one you simply cannot factorize it like the way you did for the previous one. So this is an example of quotient or ratio. If it asks you to find f prime x, how do you find it? So this is the thing that we need to learn now. So quotient rule here, this is the general rule. So you have one function on the numerator, you have another one on the denominator. On numerator, we call it ux. On denominator, we call it vx. Let's go back to this example. So this one is ux. The denominator value, which is x plus 1, is vx. Okay, that's how you read it. Okay, now, how to find f prime x or slope or instantaneous rate of change? Okay, f prime x here, you look at it carefully, yeah, because I don't want you to make mistake. You see the denominator, which is vx. Vx, you rewrite it again here, but the whole thing you square it. Can you see? And then on the numerator, you have ux, you have vx. So you rewrite vx as usual, but you differentiate ux. That's the first bit. Okay. Then you write minus. After you write minus, you keep ux, multiply by, you differentiate vx, becomes v prime x. You get me? And then you simplify as usual. Okay? So example here is, let's say we have a fx is x squared minus 4x over x plus 5. Don't factorize it, yeah, because it will make your life complicated here. Okay, now, so how to find f prime x here? So using this one is ux, this one is vx. So we know that, so f prime x is equivalent to, we write again the denominator as vx squared, isn't it? But here specifically, because it's given specifically, so we can rewrite it as x plus 5 square the whole thing. And what about the numerator? This is vx. We write it again here, x plus 5, but you differentiate the ux here. So when you differentiate ux, it becomes this. X squared becomes 2x minus minus 4x becomes 4. I'm referring to this, yeah? So that's what happened here. So this is basically u prime x. This is basically vx. So I'm done with this bit. Now minus. Let's do this bit. This bit, you rewrite again ux as usual, x squared minus 4x, but you differentiate vx, which is this. when you differentiate bx, x plus 5, x here, when you differentiate, it becomes 1. 5 here, when you differentiate, it becomes 0. Let me write it clearly because otherwise you can't see. 4x, so it becomes 1. So this one is v prime, sorry, is it? Yes, v prime x, and then this one is ux. How do you get 1 for v prime x? Again, you know that v is x plus 5, which is this. You differentiate x, becomes 1. You differentiate 5, becomes 0, isn't it? So 1 plus 0, 1. So that's why I write it this way. Okay, clear? Now, how do I know that I differentiate x becomes 1, I differentiate 5 becomes 0? Because let's go back to the previous rule that we have done. So you have coefficient rule, you have constant rule. For 5, I use constant rule. For x, I use what? I use power rule. Because x here, which is this, not this one, yeah? Because for x here, when you differentiate, it becomes x1 minus 1, 1, isn't it? Which is x equal 0, 1. So that's why you get 1. For 5 here, because you don't see x, so it becomes 0. So 1 plus 0. You get me? Alright, so I'm using the rules that we have studied earlier to do the rest. Alright, now. And then what you can do is to simplify further the answer. When you simplify further the answer, okay, let me erase the pages so that you are not confused with so many writing bits here. Okay, now here for this one, expand it, so it becomes what? 2x squared plus 10x, okay, minus 4x minus 20, and close the bracket. So I've done this bit is this. I'm expanding it. Minus, minus, minus. Okay. Then I have this in bracket x squared minus 4x. And then on the denominator, is x plus 5 squared. You see the step that I do first, second, equal sign, and then the next step, simplify it even further. Alright, 2x squared plus 10x minus 4x minus 20. Then write minus here. Can you see I'm opening the bracket? When I open the minus, when I open the bracket for x squared minus 4x, minus meets x squared becomes this. Minus meet minus becomes plus. And then 4x. And then the denominator, we write it again as usual, x plus 5 squared. And then, because I don't have enough space, I write the last line here. Equals to, simplify it further, x squared plus 10x minus 20 over x plus 5 squared. Okay, so that's it. That's the answer. Okay, now if you see here, I'm done with quotient rule for the first example, which is A. What about the second example, which is B? I just guide you. So for the second example here, find f prime x when x is equivalent to 3. So for this, you need to find f prime x the same way that I did for the first question. After you found it, substitute x back into the answer and solve it. Then you're going to get one final number, one value, not just don't leave it like that. That means you substitute x equivalent to 3 back into your answer to get the final answer. Can you try it? And you can imitate the textbook basically, yeah? Alright, so here I leave it to you to do it. Okay. Now, we are done with that one. Now, we move to the next one, which is what we call chain rule. Okay, this is chain rule. Chain rule here. But before I proceed, yeah, be careful with what you are doing. especially when you're dealing with bracket, open the bracket, after you open the bracket, minus meets plus and meets plus meets minus and whatnot, because if you wrongly open the bracket and then didn't check the sign, then you may get wrong answer. Plus minus is plus minus sign here, I mean plus minus sign, so be careful. Alright, now let's move to the chain rule. Okay, the chain rule and its relation to the power rule. Okay, the chain rule can be used if you to find the derivative or the instantaneous rate of change or the slope of a function if the function itself is a composite function. What is a composite function? A function inside a function. In the simplest way, it is known as a function inside a function. Okay, so chain rule is this formula basically. But before that, you need to really understand composite function. If we talk about, I'm talking about composite function now, yeah, I'm not talking about the chain rule. I'll introduce the composite function again, then we use chain rule to find the slope of composite function. So I'm talking about composite function, a function inside the function. So let's say if you have fx, I'm using straightforward example, 3x squared, and then I have another function gx equivalent to 2x minus 1. Okay, now if I have this capital Fx is written as f as a function of g, f as a function of g. This one is gx. Gx is what? Gx is this. I can rewrite this new function as this, f capital Fx, f as a function of g. My g is what? My g is 2x minus 1. So I just need to substitute gx with this one. So 2x minus 1. So fx is capital Fx is a function of small letter fx. Okay, which is this. But this is still generic. Yeah, this is not specific because you still have general term here. So you make it specify because you know it is this. Now what you can do, fx, the whole thing here is fx, isn't it? So fx is given by this. Okay, be careful. Yeah, you look at the way I write it. So here. So how to write composite function? Fx, 3 is 3. Now this one, gx, is the x itself, isn't it? Because the whole thing here, like I said just now, is fx. What is x now? X is the whole thing here. Inside here, 2x minus 1. So here, 2x minus 1, x is x, and then put square. That's it. Is it clear? Okay? Alright, so that's your final form of your composite function after you make it specific using these two information. Okay, that's the example of composite function. Now next, if we have this kind of composite function, how do we find the derivative? So this is our objective now. Go back to our objective. Alright, then we can use chain rule. And there is another rule that can be related to chain rule for this specific composite function, which is power rule. Okay. So in general, if f and g are differentiable, can be differentiated with y equal to fu, such that u is gx and y is differentiable function of x, and therefore you can find dy over dx equivalent to f prime u times g prime x. Okay, or equivalently dy over dx equal to dy over du times du over dx. Now remember again, here they use d instead of delta y. They can use it because all of the function only have one independent variable, which is x. Had it been many different independent variables, they cannot use d, they have to use delta instead of d like this. You get me? I did mention to you in the previous slides. Yeah. Okay. Now, so here, to make your life easier, let's go back to the example so that we can solve it. But here, I'm using this example, much easier. So here, find dy over dx. So if your y is given by this, square root of x squared minus 1. Before I find the slope or dy over dx, I know that I can rewrite this original function into another form which is similar. That is x squared minus 1. So it becomes to the power of 1/2 or similar to this. So this is actually similar to this. So if I use chain rule, dy over dx, look at this carefully, yeah. Power, we write again the function, the power that we have 1/2 minus 1, and then next multiply by what? Multiply by the derivative inside here. The derivative inside here is what? X squared becomes 2x, minus 1 becomes minus 0. That's it. Isn't it? Okay. Now, it becomes what? 1/2. We write again this. Okay, and then this one becomes minus power of minus 1/2. And then you have 2x. Now, we are done with the derivative, but we need to simplify the function. So don't just leave it just like that. 2x 1/2, I can cancel 2. Okay, I can have x squared minus 1. I show you one by one here so that you don't miss the step. And then you have x. It can also be written nicely like this. X, but because this one is power of minus 1/2, you can bring it to the denominator. We write it again. You can write it this way. Some people can also write it this way. Up to you. You can write this way or you can write this way as your final answer. That's it. Okay. So you can see here when I did my chain rule, when you look at the formula, dy over dx, dy over du, du over dx. Okay. So then there is a question, where is my du, where is my this and that, isn't it? Okay. So I'll show you more after this, yeah, because it has something to do with power rule. So if I were to explain to you a chain rule here, the concept is not so clear. Alright, now, so let's look at another example. The chain rule here in relation to power rule with another different example. The chain rule is very useful and will be extremely important with functions that we will study later. So here, there is a specific types of chain rule, we call it power rule. And in fact, that one I have done it here. Let's go more into detail so that you can easily understand why chain rule, a specific case of chain rule is called power rule. So it is a very useful algebraic function because, we can use it for composite function outside the power. So here, if you go back here, this is one function. So this, let me erase this here. Okay. Inside here is one function, and then here is another function. This function is inside this bigger function. I mean, bigger function is square root. Inside square root function, there is another function. So you can see it is a composite function. So for any kind of composite function, alright, to do derivative using chain rule, the more specific one is power rule. Okay, so if it is power rule, as you can see, if y equivalent to u to the power of n, where u is differentiable, you can differentiate it, then the formula looks like this. Dy over dx is equivalent to n. You see here the power n, same as power rule. Bring n here, u to the power of n minus 1. But because inside u you have x, remember this, then you differentiate one inside. That's what we did just now. Alright, so let's say I'll show you more, yeah, in terms of examples so that you can see which is which. Okay, so let's say we have this power rules with radicals, for instance, or this one, or let's go back to the simplest one first, so then only we go to that one, yeah, otherwise it becomes complicated for you. If you see this one, we did chain rule, but specifically power rule, because first what I did was so that you can see why it is called power rule, specific for chain rule. Original equation looks like this, but I can convert it to this because this is just similar to this, isn't it? Can you see power here? But the thing here is that inside you have x and some other numbers. So it's not like y equivalent to x 1/2, you know. It's actually y equivalent to x something something to the power of 1/2. You get me? But they look like similar, isn't it? Like the one that you learned for power rule for the basic one previously. So that's why we need to have chain. Okay, the chain here. That's why, as you can see, when we differentiate it, okay, let me erase first. This. Oh my God. Okay, this. Okay, so as you can see here, when I differentiate it, I differentiate it the same as power rule. You see this one, y prime equivalent to, you bring 1/2 here and then you write x 1/2 minus 1, isn't it? Same thing that I did. I bring for this one 1/2 here and then I rewrite again the original function here, alright? And then the power here I minus 1, which is similar to the simplest power rule, isn't it? Just similar. However, because inside here I have x squared minus 1, okay, then it's unfinished work. So I have to differentiate it. How do I differentiate it? Multiply here and then put in bracket, differentiate the whole thing as usual. X squared becomes 2x, minus 1 becomes 0. Constant, isn't it? Alright, so that's how we do it. So as you can see here, it is power rule, specific types of chain rule, which is power rule, because it's similar to the basic power rule that we learned earlier, which is this. It is chain rule. Why? Because it has some tails here. This one is another tail because this one is unfinished work. Do you get me? Alright, and then the rest you just solve as usual. So that's power rule basically. Okay, and then for this one, A, okay, so you can see here, this is also composite function. This is the inside function. Inside the whole thing is another function. So the big thing is a function of the one inside. So it's a composite function. This one you can also use power rule. But here you need to rewrite again the function so that you can see clearly it can be done with power rule. We write again constant 3 in bracket x squared minus 3x plus 1. Then it becomes to the power of 1/3, isn't it? So when you want to find y prime, 3 is a constant, keep it just like that. The whole thing here to the power of 1/3, then you can differentiate it using power rule, okay, like this. So this one here is u. So you differentiate u, constant stay the same. So here x squared minus 3x plus 1, and then bring 1/3 here. So because the space is not enough and it's not clearly nice, so I change multiply by 1/3. There you go. And then this one, the power 1/3 minus 1. But because inside here you don't just have x, but you have some other things, x squared minus 3x plus 1, then you multiply inside, you differentiate as usual. X squared becomes 2x, minus 3x becomes 3, plus 1 becomes 0, because it's a constant when you differentiate, then that's it. You simplify further, 3 times 1/3, you can cancel, so it becomes, you know, x squared minus 3x plus 1. 1/3 minus 1 becomes minus 2/3, isn't it? Multiply by 2x minus 3 in bracket. So how are you going to simplify it further? It can be rewritten as this. 2x minus 3 over x squared minus 3x plus 1 to the power of 2, that, isn't it? Or because I don't have enough space, so I write it this way. So you can also rewritten it as this 2x minus 3 over this x squared minus 3x plus 1 in bracket square, because this is just similar to this one. You get me? Alright, so that's it. Okay, now there are some examples that we can look here for the derivative application, some of it, yeah. Alright, so let's say the demand for x 100 units of a product is given by this, x equivalent to 98 times 2p plus 1 to the power of minus 1 half minus 1, where p is the price per unit in dollars. Find the rate of change of the demand with respect to price when p equal to 24. So you can see clearly here, it has power, but inside it you still have 2p plus 1. It's not just 2p. You get what I mean here? So you can use power rule specifically for chain rule to find the rate of change. Okay, instantaneous rate of change. Once you find the rate of change, substitute p equivalent to 24 to solve what is x prime equivalent to what value. So first, differentiate x here with respect to p. Okay, let me erase this first. Otherwise, okay. So we need to find the rate of change. In other words, we need to find x prime, or in other words, you need to find derivative of x with respect to p. Once you find it, plug in p value equal to 24 into your answer and then solve it. Then you can find specific x prime for specific price at 24. Now, because I said this one here has a power and you still have variable here, you can use chain rule, specifically power rule for chain rule. Okay, now let's do it one by one. So 98 is a constant, leave it just like that. Minus 1 half, I bring it here because I'm doing, differentiation. 2p plus 1, you write it again. Minus 1 half, minus 1. But here, you differentiate it. Multiply by differentiation. 2p, differentiate becomes 2. Plus 1, differentiate becomes 0. So, I have 2 only. Alright. Then, I can simplify it further. Don't forget here, when you have minus 1, you differentiate it, it becomes 0, isn't it? So that's why I didn't write it earlier, in case you wonder where minus 1 goes. Okay, now next, I write it here. 98 and minus 1 half can be divided. It becomes what? Minus 49, isn't it? And then here, 2p plus 1 minus 1 half minus 1 becomes minus 3 over 2 times 2, isn't it? Or actually, rather than writing like this, I forgot that there is this, so I don't have to multiply by 2. Okay, otherwise it's not efficient, basically. So minus 98. So we are left with that. And then you substitute p equivalent to 24 and then solve the rest. Minus 98, 2 times 24 plus 1 to the power of minus 3 over 2. This one, I don't want to solve it. You just solve it yourself using calculator. Then you get some answer here, yeah. Once you get some answer here, and make sure you know how to interpret. Okay. If, let's say, if I don't know what's your answer and I don't even know the right answer because I haven't calculated it, I leave it to you. Let's say this is just a hypothetical answer. Okay, let's say the answer here is minus 105. You see here the demand. This is demand. Quantity depends on price. Okay, so minus sign here, if you study economic, you know that quantity depends on price, they are negatively related. That's why it has minus sign. And this answer here is just hypothetical. Like I told you just now, I haven't calculated it. You need to find it. If let's say the answer is 105 minus the and that's it. But I'm sure this is wrong, but I just want to emphasize on the interpretation. You need to know how to interpret. Okay, if you get answer minus 105, what does it mean here? If price increases by $1, then quantity demanded, which is X, decreases by 105 quantity. If it is kilogram. If it is, bags, 105 bags. The negative sign here shows you the direction of the relationship between X and P, quantity and price demanded. And in the study of economics, this is basically law of demand. Okay. All right. So I hope this is clear. And here, when we talk about the using derivative formulas, for this kind of expression, you can see clearly that we can use power rule, specific power rule, for chain rule, isn't it? But we haven't found, let's say, instead of this, let's say your function looks like this. This is A, this is B, and then A times B, and then the whole thing to the power of 5. So this function is, of course, obviously different from the first one, isn't it? Why? Because the whole function here, both of them are raised to the power of 5. But then, it consists two functions instead of one function. Here you only have u to the power of n. Remember, for this one. Okay? But here, you have A, you have B, not just one. So here, so this function is obviously different because the function u, which is raised to the free power, is the product of 2. The product means what? You can see clearly, product means multiplication, product of this A and this B, isn't it? Alright? So how to do it? Alright? So how should we proceed? That's my question. How we solve it? We consider that is this as a function of y. So here you can see the function of y consists of two parts, the first one and the second one. And these two are next to each other and they are multiplied. Because they are multiplied, so we can consider that y as a product of two functions multiplied. Okay, so and then the first one here is with power, which is 5. Alright, now because it is the product of the two functions, okay, so we can basically apply power rule, product rule. Let's consider this one as ux, let's consider this one as vx. So we already know the formula for differentiation or derivative. So in this case, then you know that y prime equals to fx times g prime x plus fx prime times g x. Okay, now so here, since this one is ux, this one is vx, let's solve it. So the product rule gives us this generic function. So v is this one. Let us rewrite ux again here, which is this. And then we differentiate vx with respect to x. So when we differentiate it, x cubed become 3x squared. I hope you know by now how to get 3x squared. X becomes 1 and then 1 becomes 0. So that's why we are left with 3x squared plus 1. Okay, done with the first part. The second part, now we differentiate this, we leave this alone. Okay, when we differentiate the first one here, x squared plus 1 to the power of 5, then we can use power rule in the chain rule. You see this one? This one is actually vx that is not differentiated. This one is a plus sign product. Yeah? So here, If you want to differentiate, it becomes like this. How it is done? 5, bring it to here, to the base, and x squared plus 1, write it again. But power 5 here becomes 4 because 5 minus 1. Okay? And then 2x. Why? Because the one inside here has to be differentiated. So that's why you get 2x. So that's how we do it. I do one by one slowly. So this is a mixture between product rule, power rule, and also chain rule. Okay? Now, so basically after that, don't just leave it like that. Yeah, you can simplify it further to make it nicer. So let me erase this mess first. So as you can see here, this power rule is used here. Okay, is used here. Power rule for chain. Okay, so we can simplify further this answer, simplify further, and because we have common factor, and that common factor is actually x squared plus 1 to the power of 4. If you see this, the highest factor is 4, isn't it? So here you can factorize both of them, this one plus this one, okay, and you'll get something like this. So if you try to find the answer by factoring x squared plus 1 to the power of 4, so it becomes like this. So you take out x squared plus 1 to the power of 4 here, and then the rest looks like this, isn't it? And then you simplify it further. Okay, so that's for the product of two functions involving power rule and product rule. Next, we want to look at the quotient or the ratio of two powers. So if you have a quotient or a ratio function, what should you do here if you want to find the slope or the gradient or f prime x or y prime x? Okay, what you can do here is that we can use quotient rule, and we know that quotient rule looks like this, isn't it? Okay, Vx here, square it, and then here what you can do, Vx times Ux tolak Ux times Vx V. So next we do it on this question. So I continue here, yeah, because I don't have enough space to write. Alright, so here it becomes f prime x, okay, equivalent to, on the denominator is Vx squared. In this case, it is x to the power of 4 plus 3 to the power of 3, and then power again square. What about the numerator? The numerator, let's assume that this is Ux, this is Vx, okay, Ux and Vx. What you can do is Ux and Vx. See, I forgot to put this. Okay, so you have here Ux prime and then multiply by Vx, isn't it? And then you minus Ux and then multiply by V prime x. Let me write it properly here. Okay, so in this case, for the first one here, how do we write? And for the second one here, how do we write? Let's look at it. We differentiate ux first, which is this one, but we write this one as the same. So here we have x to the power of 4 plus 3 and then cube, but we differentiate this, it becomes 2 and then x minus 1, and then this one becomes power 1 because 2 minus 1, and then you differentiate the one inside, becomes 1, isn't it? Okay, and then write minus. So what we have done here is that we use power rule, because this one is power when you want to differentiate it. Okay, now next, after minus sign, we differentiate Vx, but we rewrite again Ux as usual. So Ux is this, and Vx prime. So Vx prime becomes what? So we use power rule again, because if you can see here, this Vx has power, which is a cube, x to the power of 4 plus 3 cube. So when you differentiate it, you bring the power here, 3. We write again the one in the bracket, x to the power 4 plus 3, and then 3 here minus 1, and then the one inside here, you differentiate it, it becomes what? 3x to the power of 3, or 3x cubed, and then you close the bracket. Okay. Okay, so you have 3, sorry, it's not 3, yeah? It's 4 actually. Let me write it properly here. So x to the power of 4 becomes 4x 3. Do you know how to get this 3? Because this power becomes 3 because 4 minus 1, yeah? So can you see, I close the bracket first. Can you see here, this one is ux, but this one is vx, v prime x. We use what rule here? Chain rule, but specific power rule for chain rule. Can you see? So once you get this, you can do more arithmetic operation to make it simpler. So here you have what? Let's look at this bit. Okay. We can basically simplify it further, becomes like this. So 2x cubed plus 3. So 2x to the power of 4 plus 3 cubed. Okay, and then you have x minus 1, and then you have minus sign, which is this. Okay, minus 3 times 4 becomes 12x cubed. Okay, and then you have x minus 1 square, which is this one, and then you rewrite again this, it becomes x to the power 4 plus 3. 3 minus 1 becomes 2. Can you see? And then divided by denominator, which is x to the power 4 plus 3. You see power here, 3 and 2. You multiply them. Okay, basic maths, yeah, becomes 6. Okay. So the first here belong to anything before minus sign. Okay. The second bit here after minus sign is this. Okay. I hope this is clear. See them carefully. Look at them carefully. Now here we can simplify it further. Why? Because you have common factor. For instance, x, what's the common factor here? X to the power 4 plus 3 to the power of 2 or square, isn't it? Because we have 3 here, we have 3 here power, we have 2 here power, we have 6 here power. The lowest power is 2, so that is the common power for x to the power of 4 plus 3. Okay, another common factor here is 2. Okay, 2, 12, we can factorize, isn't it? Another common factor here is what? X minus 1. Here you have x minus 1 to the power of 1. Here you have x minus 1 to the square. So the common factor here is x minus 1 to the power of 1, isn't it? So now we can factorize them, numerator and denominator, so that we can reduce the form of fraction. So if we reduce the form of fraction, then it becomes nicer, isn't it? So how it looks like? So I rewrite it again here by reducing, by factorizing it. So here I take out the common factor. The first common factor on numerator is 2. The second common factor is x to the power of 4 plus 3 to the power of 2. The next common factor is x minus 1. So we have 3 common factors. And then the rest we do like this. X to the power of 4 plus 3. And then minus 6x cubed, x minus 1. Isn't it? Okay, please see them carefully. And then down here, x to the power of 4 plus 3 to the power of 6. You know that this and this can be simplified for the 2 and 6. So this one vanished, this one becomes 4, isn't it? So then we can rewrite it again, becomes like this, 2x minus 1. Okay, and then furthermore, not only that, the 1 in the square bracket here, we can also simplify it further. Then you get minus 5x to the power of 4 plus 6x cubed plus 3. Okay. Plus here, yeah. And then this one becomes what? Becomes 4. Okay. So from this step to this step, be careful, yeah. We have 3 common factor on numerator, 2 common factor, which is this and this, three common factors from the numerator. There are 2x to the power of 4 plus 3 square, and also x minus 1 in bracket. And these three among these 3 common factor, this one can simplify this, isn't it? So that's why this one, x to the power of 4 plus 3 here in bracket to the power square or to the power of 2 is actually not appearing here because it has been cancelled with this one left with 4. And x minus 1 is this, 2 will stay the same, but what happens to the 1 in the square bracket here? After simplification, we get minus 5x to the power of 4 plus 6x cubed plus 3. Figure it out how to get this one. Yeah, this is very simple already. Okay? So that's the answer for this a bit complicated exercise here. Now let's look at another more practical example. And this practical example is about revenue. Let's look at this. Okay. So suppose that we have the weekly revenue. Okay, function for a product is given by this. Yeah, Rx equivalent to 36 million x over 2x plus 500 square. So you have quotient and quotient, equation here, and then you have numerator with x, denominator also with x but square. So what can you do here? So here we need to find what? Find the marginal revenue function. Marginal revenue function means r prime x, yeah? So in order to find this, you need to find r prime x using quotient rule. And then after that, find the marginal revenue when 50 units are sold. Once you find this, insert x equivalent to 50, get how the marginal revenue when 50 are sold. Alright, so how do we do it? We do it slowly here, one by one. let's see this one. Okay, so we know that marginal revenue is equivalent to R prime X. Okay, so we can use quotient rule. In order to use quotient rule here, let's go back to the question. Okay, the question says what? The question says that Rx is equivalent to 36 million X. Okay, 36 million X over 2X plus 500 in bracket square. Okay, so let's go back to this because we want to solve it. So here, but before this, otherwise you cannot refer to which one. So let me rewrite again the original function. So Rx here is given by 36 million X over 2X plus 500 in bracket square. So we need to find R prime X, which is marginal revenue. Because it's quotient with X on both numerator and denominator, then we need to use quotient rule. Now let's do it one by one. So this one is UX, this one is VX. So let's differentiate UX but leave VX as usual. So here 2X plus 500 square. When you differentiate 36 million, it becomes 36 million only. 36 million X, you differentiate becomes 36 million. And then you put minus sign. Now, you rewrite again 36 million X, but multiplied by the derivative of Vx or V prime X. When you differentiate it, you see power here, you see X here, then we can use chain rule. Specific chain rule here is power rule. Okay, so when you do that, do it one by one. So because I don't have enough space, I have to do it carefully here. Okay, so it becomes in bracket. You bring 2 to the base here, it becomes 2. We write again 2x plus 500. The power 2 here becomes 1, isn't it? And then you multiply by another 2. I don't have enough space, so I write it this way. And then close the bracket. Let me rewrite it properly then, otherwise you don't get it. It's too messy. Okay, so it becomes like this. Minus 36 million, and then in bracket you differentiate Vx becomes V prime X. You bring 2 here to here, and then put bracket 2x plus 500. The power 2 becomes power 1. Okay, but actually I don't have to write it. Okay, 2 minus 1, 1, yeah? And then we have 2x here. When you differentiate inside, then it becomes 2. Close the bracket. Do you get me? And then don't forget the denominator is 2x plus 500 square. Okay. And then you solve it until you get it. This one is just a matter of calculus. I hope you can get it. Show all the steps. And then finally, after certain step, you're going to get this. There are some steps here that you have to write, yeah? But I just jump into the final answer. The final answer is 36 million in bracket 500 minus 2x over what? Over 2x plus 500 cube. Okay, cube. So here I think I made mistake basically. So let me show you this mistake so that you realize it. Okay, let's go back to the original function. If you see original function, it is square here, isn't it? When you write the denominator here, it should be squared as well. So it should be this. Okay, this is what I mean. It's not square here because you double it. initially it is correct square, but here when you differentiate using quotient rule, then instead of 2, you make it 4. Instead of 3, okay, this one is correct. This one is what? Once you have done it, you corrected it, then it becomes 3. Okay, and that's the correct one. Because this one is original one. When you write in differentiation using quotient rule, this one becomes 4 instead of 2. 2 times 2. Okay? Alright, and then this one, because of arithmetic operation, that's why it becomes 3. Now, I have answered question A. Now we move to question B. Question B says, if you have found marginal revenue like this, what is the marginal revenue if your quantity is equivalent to 50? So what you can do here is that once you get this 50, once you get this answer for marginal revenue, this answer, you insert x equivalent to 50 here, and then you solve it. Then you can get marginal revenue. Yeah? Show all the work. And then finally, you're going to get 200 over 3. Or if you write in decimal point, you get 66.6667. Keep up to 4 decimal points. Yeah. So if I were to interpret this result, what does it mean here? It is if quantity sold increase by 1 unit, then my revenue will increase by $66.6667. Okay? Now that's how we apply for marginal revenue in the study of business. Okay, before that, I would like to, before other things, I would like to show you this summary here. So this table presents you what to do basically for different types of primary function, how to do, differentiation to find derivative. Same with this one here. So here, if you have constant, then f prime x becomes 0, isn't it? But if you have power here, then you have, but if you have power here, then you have this. If you have this, then you have this. All of this has been discussed earlier, and it gives you generic form here. So same with this one. So I hope you look at these, tables, try to see and apply them. And now we move to the last bit of, the derivative. We move to higher order derivative. Higher order derivative means after you get, let's say you have primary function fx, you differentiate it, you get f prime x, isn't it? Let's say this one is 5x squared, you differentiate it, becomes 10x, isn't it? Now, you can also differentiate this and it becomes f double prime x, isn't it? So 10x, you differentiate it, it becomes 10, isn't it? But if you want to differentiate further f double prime x here, you differentiate it further the third time, because you don't see x here, using constant rule, and it becomes 0, isn't it? And then it stops. So this A and B are the example of higher order derivatives. What's the use of having higher order derivatives? Of course, it has some meaning. Yeah. For this one, it shows you the shape of the slope. For this one, it shows you the slope. Let's say you get 10x. Okay. If it is this one is actually second derivative. This one is actually first derivative. This one is third derivative. Okay. So the second derivative is actually a derivative of the first one. Okay. So you differentiate twice, you call it second derivative. You should differentiate it the third time, the third derivative. Okay. Now, why don't we look at some example here? Find the second derivative of y equivalent to x to the power of 4 minus 3x squared plus x to the power of minus 2. So here, how do you do it? To find second derivative, you must find first derivative first, isn't it? Otherwise, you can't find second derivative. First derivative, x to the power of 4 becomes 4x, 3. I hope you know how to do this already. Eh? Minus 3x squared becomes 3 times 2x, isn't it? Plus x to the power of minus 2 becomes minus 2x to the power of minus 3, isn't it? So here, because I need to find the second derivative, so I don't simplify it. I just differentiate it once again, so it becomes what? 4x cubed becomes 12x squared minus this one 3 times 2 6x becomes 6, isn't it? And then this one plus minus 2, bring minus 3 here, minus 3x to the power of minus 4, isn't it? So you can simplify it now. 12x squared minus 6, okay, plus 6x to the power of minus 4. Or we can simply rewrite it as what here? 12x squared minus 6 plus 6 over x to the power of 4. So this is our second derivative. What does it mean by second derivative? It will be explained further later. Yeah. So here we can also have third, fourth, fifth, and higher derivative continuously, indefinitely, until you get the final one, the answer 0. When you finish all the variables, okay, then you stop. This is one way to write it, like I did just now. Another way is this way. Another way is this way. If you have this, that means you differentiate it 4 times. One way to write is this, this, or this, and so on and so forth. So, for instance, find the first 4 derivative of this. So, you need to find the first derivative, 12x squared plus 10x plus 0. Find the second derivative, 24x plus 10. Find the third derivative, 24. Find the fourth. What do you get? You don't see x, isn't it? Then you get 0. That's the final answer for this question. So first 4 derivative, first derivative, second derivative, third derivative, fourth derivative. Is it clear? Okay. And you can also do it using this example here by using International Telecommunication Union and Key Global Telecom Indicators data from 1990 and projected to 2020. The billions of world cell phone subscriberships can be modeled by the function here. So where t is the number of years past 1990. All right. So this is basically the t, remember the number of years. CT, remember phone subscriberships, how many subscriber over the years. Okay. Find the instantaneous rate of change of the worldwide cellular subscribers function. When we talk about instantaneous rate of change, this is another term for derivative. Okay, so how do you find it? So you need to do C prime t, or can also be written as delta C t over delta t. I write it properly, yeah, because some student would imitate my drawing differently. It's not like this, you know, it is delta. So here, this one, when you differentiate it, it becomes minus 0.895 times 3. Okay. And then t to the power of 2t squared plus 30.6 times 2. And then t, because now it's left with t, because 2 minus 1 becomes 1. Plus 2.99. That's it. So we have answered question A. Find the instantaneous rate of change of the function found in part A. You have found the answer here in part A. You find instantaneous rate of change for this one. So that means you need to find C double prime T. Okay. So, but this one I haven't finished answering it. You have to simplify it plus what here, then you get the final answer. And then once you get this answer, differentiate it once again to get answer B, because the question is asking you about the same thing but using this one, not this one. Okay, is it clear? So I hope you can try it at home. Here I'm not going to show you because it's just a simple calculation basically, unless if you forgot the rules of the derivatives or differentiation rules. Okay, For what t value does the second derivative of ct equals 0? So here what to do? I just guide you here. You have found the answer for this, isn't it? Whatever. Okay. And then ct equal to 0, set it equal to 0. So you have t inside here. You rearrange it until you get t equal to 1 to make c double prime t equals to 0. Okay. What about this? What about this? Can you try to figure out the answer? Explain the meaning of c prime 25 and c double prime 25. Okay. If it is c prime 25, this is the first derivative. This is the second derivative. This is instantaneous rate of change of CT. This is instantaneous rate of change of C prime t. We know that C prime t is also known as instantaneous rate of change or derivative. So how do you differentiate? How do you interpret the result? Can you figure it out? I may ask you in the quiz, All right. So that's it for now. We'll see application of derivative more later.